sharing, you can.
Yes.
Great.
Perfect.
Yeah, now it's sharing. Okay.
Perfect.
Great. Okay, well, thank you very much for the invitation. I'm really glad this is moving forward despite the very difficult and crazy times. I hope that everyone is managing and staying sane and safe. So today I'm going to talk about the cosmic censorship conjecture, which originally was a conjecture about general relativity. And the reason that I've tacked on the quantum there is because recent evidence has come to light that suggests that cosmic censorship as a conjecture is not necessarily true about general relativity, but might be true about quantum gravity, and in particular might be true about solutions to GR which admit a UV completion in a consistent quantum theory of gravity. So with that brief motivation in mind, let me begin with a puzzle. So here are 3 fun facts. The first one is that generic solutions to the Einstein equation have singularities. The second fun fact is that we have never observed the formation of a singularity, ever. And the third one is that Einstein's equations describe the observable universe pretty well. And if you think about these 3 fun facts for a moment, you'll quickly come to the realization that there's a bit of a tension between them. And the way that this tension can be resolved is by noticing that in our universe, empirical evidence suggests that singularities are hidden behind event horizons, which allows us to make sense of how all these 3 facts can be true at the same time. The way of settling these 3 fun facts led Roger Penrose to conjecture the existence of a cosmic censor. So in very fanciful language, the statement that,
I mean, is it really fair to invoke experimental observation as in favor of cosmic censorship? I mean, we only have seen black holes in the last few years, and there's lots of things out there that could potentially be naked singularities. That seems a leap.
Absolutely. I wouldn't call it a justification of cosmic censorship so much as a partial motivation. Another motivation, which historically is more accurate, is that of all the solutions that were known at the time, it seemed to be the case that singularities were always cloaked behind event horizons. Since that's no longer true these days, it's difficult to motivate it from that perspective. And so instead we can say, well, of the observable universe, there doesn't seem to be any naked singularities, although of course that's based on current evidence, which is by definition limited.
Wait, are you including also the Big Bang in that case or not?
No, so I will mention briefly the initial singularity. Mostly what I'll refer to here are singularities that are a result of dynamical processes like matter collapse.
Right, but we can see in principle, we can see all the way to the Big Bang.
That's right. So here really what you will, I'll say a much more precise version of cosmic censorship in a moment. And it really is, the technicalities of it will allow for Big Bang singularities while forbidding a singularity that of the type where matter just coalesces into a very large time-like naked singularity. So this is the rough idea, but you're right that the Big Bang is indeed, but put in here, except initial singularity. Can you see if can you see the cursor, by the way, when I highlight something?
Yes, we can see it.
Okay, great. So yes, you can see this except initial singularity, and in a few slides, I'll give a precise version of this, which hopefully will be clear why the initial singularity is not a problem.
And what do you have in mind when you say that we have counterexamples now to cosmic censorship?
So if you will give me a few more slides, then I'll talk about what those counterexamples are. But just to briefly answer your question, I'm talking about first beginning with things like Gregory Laflamme and Myers-Perry black hole, black rings, and also about the more
nothing in 4 dimensions.
So in 4 dimensions, I'm talking specifically about the examples of Horowitz, Crispert, and Santos, 4-dimensional ADS. So let me
nothing in 4-dimensional flat space, which is where the conjecture was originally formulated.
That's right. So if you'll just give me a few moments, I will get to that. I have a slide on that, and I will get to 4-dimensional asymptotically flat space. Just give me a minute, okay?
Okay.
So just to finish, this is the broad scale of motivation. I'll get into the details. I'll hopefully answer these questions in just a few minutes. But one aspect of this cosmic censorship conjecture is a bit of a double-edged sword, because on the one hand, it would explain why we haven't seen a naked singularity in the universe, On the other hand, it would mean that we could never, if it's true, we could never observe strong quantum gravity physics from a naked singularity. But of course, as physicists, we don't get to pick what nature does to suit our purposes. If cosmic censorship is true, it's just true. And our job is to determine whether that's the case or not. So is it true? So to address Andy's question, indeed, cosmic censorship looks pretty good in four-dimensional asymptotically flat space. But there are counterexamples to cosmic censorship in higher dimensions and in spacetimes with different asymptotics. So let me just say one more word on that. So there are two possibilities. Either something is very special about four-dimensional asymptotically flat space, or these counterexamples actually do exist in 4D asymptotically flat space, and we just haven't been able to find them. I don't think we have good evidence in favor of either conclusion at this point. I think either one is fair game. Now, one important point is that cosmic censorship might be something which is true about nature, but nature at the end of the day is not actually general relativity. So nature is really described by quantum gravity, and not all solutions of GR are good low energy limits of quantum gravity. So one possibility is that quantum gravity is what enforces cosmic censorship. And if quantum gravity indeed prefers to high singularities and strong quantum gravity behavior behind event horizons, then quantum cosmic censorship would be a very deep fact about nature. So how can we figure this out? How can we investigate better whether there is a quantum cosmic censorship which is true in quantum gravity? And so this is what this talk is about, and I'll begin with some background, which I think hopefully will address some more of the questions that were asked earlier. So this is again, the not very precise formulation. Naked singularities are invisible to an asymptotic observer other than an initial Big Bang singularity. So this was more or less Penrose's conjecture in 1969. Now, the more precise version, which I've written in fine print here, so this is for the relativists and mathematicians in the audience, is that this is due to Garish and Horowitz, and there's an ADS version, which is more recent, which is that the maximal Cauchy evolution of a set of generic asymptotically flat or asymptotically ADS initial data is asymptotically flat or asymptotically ADS, strongly asymptotically predictable. In particular, this means you have a complete square plus or a complete conformal boundary in the case of ADS. So here I've given an example, I've drawn an example of a conformal diagram of something which is an asymptotically ADS spacetime that badly violates cosmic censorship. So here we have a time-like boundary. So this is a Penrose diagram, which means that light rays travel at 45-degree angles. So this is a time-like boundary of ADS. Here we have some regular generic initial data, and it evolves to form a time-like singularity. And these dotted lines here, this is the Cauchy horizon. So in other words, the maximal Cauchy development of this slice gets up to this over here. And asymptotic observers over here are perfectly able to see this singularity. So it's a naked singularity. And in particular, what's also true is that the manifold, the space-time manifold, is extendable beyond this Cauchy horizon, even though GR doesn't actually tell us how to evolve this Cauchy slice past this point here. So GR fails to be deterministic by a very large amount in this picture of violation of cosmic censorship. So this is what I have to say, roughly speaking, about the formulation, the original formulation about cosmic censorship. Now, let me say a few words about violations of cosmic censorship. So in 5 or more dimensions, there is a Gregory-Laflamme type instability. So this is an example of this is the black string, or if you like, since the black string is not strictly speaking asymptotically flat, you can talk about the black ring, Myers-Perry black holes. Where here I have given a picture of the black string. This is essentially Schwarzschild with an extra planar dimension. And these crusts and troughs will get progressively further apart. And so the crust will get larger, the troughs will get smaller, and eventually there's an instability which results in a pinch-off. And in the moment of pinch-off, there's an instantaneous naked singularity. So these are the Gregory-Laflamme type instabilities that exist in 5 or more dimensions. And more recently, there have also been counterexamples for asymptotically ADS4 initial data, so in 4 dimensions, but asymptotically ADS spacetimes. These were the examples that I alluded to earlier by Horowitz and Santos, and CRISPR, Horowitz, and Santos. So the initial violations, these Gregory-Laflamme black string type instabilities, these were mild in the sense that the pinch-off singularity or the critical collapse, these are small violations which you can think of as localized to Planck-sized regions. There's a vague sense in which these most likely result in quantum gravity without effects that are really visible to semi-classical asymptotic observers. So these don't seem like such a terrible violation of cosmic censorship. Maybe it violates the spirit of cosmic censorship, the letter of cosmic censorship, but it really doesn't violate the spirit of it very much. But this must suggest that there's some relaxed version of cosmic censorship that allows for these Planckian tiny little singularities by some measure of tiny, which is still valid. But the examples of Crisford, Horowitz, and Santos are rather different. And these are examples where the curvature grows without bound in an extended region. And they suggest that cosmic censorship, at least as a general conjecture about general relativity, maybe not about 4D asymptotically flat space, but a conjecture about GR, that this is potentially altogether false. What is interesting, however, is that these violations of cosmic censorship also violate a conjecture about quantum gravity, known as the weak gravity conjecture, which suggests that potentially, even though cosmic censorship can be badly violated in general relativity, potentially those solutions in general relativity in which cosmic censorship is badly violated are not valid in quantum gravity. So a possible hypothesis is that even though cosmic censorship is badly violated in solutions to GR, there's a quantum version of cosmic censorship, which is similar to Penrose's conjecture in spirit, that holds for solutions to GR that do admit a UV completion in a consistent quantum theory of gravity. Put differently, potentially quantum gravity permits the existence of small singularities, something like Gregory-Laflamme, and forbids the existence of large naked singularities. So none of this is quantitative, and as we get through the talk, it will become progressively more and more quantitative. I just want to say a couple of words about a quantum version of this. So far, I've talked about classical solutions to GR that involve only classical matter. But if we're talking about quantum cosmic censorship, we also want to be able to include spacetimes that have significant quantum back reaction. For example, the canonical case of a naked singularity in an evaporating black hole. So here is a conformal diagram of an evaporating black hole. So again, light rays here travel at 45-degree angles, and this is asymptotically flat. And so here's there's a black hole that's formed from collapse. This is the event horizon. Eventually, the black hole radiates and completely loses its mass. And out here, we end up with something which is not a black hole at all. Now, in the endpoint of evaporation, sorry, is there a question?
Well, due to the quantum nature of the particles that it's radiating, yeah. Could there be a point where you don't have enough energy in the black hole to radiate a quantum, so you might get stuck at even before you form singularity?
So you're talking about whether, let me see if I understand correctly what you're asking. Are you asking if the endpoint, if the evaporation endpoint is a naked singularity or not?
Well, they're just made, if the black hole has to lose mass by radiating away particles, there just may not be a light enough quantum that would be radiated at the very final stages. So I guess what guarantees that the evolution will go from whatever the mass of the black hole started all the way down to zero mass? Could it get stuck at a certain
let me stay away in this talk from questions from UV questions about what is the dynamics of the black hole evaporation near the endpoint, and just say that whatever happens over here is clearly very heavily ruled by quantum gravity. And so if this thing is visible to the asymptotic boundary, it would be extremely high curvatures or extremely high quantum gravity effects that are visible to the asymptotic boundary, and that we might identify that as a naked singularity. And so, but this is something which is Planckian and quite small. And so there's an intuitive sense in which maybe this is allowed in the same way that Gregory-Laflamme is allowed, where large singularities would not be. So now, cosmic censorship has been around for a long time, and so we might ask, why has it been so difficult to prove or disprove it? And one of the reasons is that cosmic censorship, in its very idea, is fundamentally acausal. So this is something that we need to understand if we're going to search for quantum cosmic censorship conjecture, which we hope might be true in quantum gravity. And so let me spend just a few minutes explaining what I mean by that. In deciding whether a singularity is cloaked behind an event horizon or not, we have to confront what is unfortunately a pretty inconvenient fact, which is the inconvenience of the definition of the event horizon. So the event horizon, let me just remind you all, is defined as the boundary of the region that cannot be seen by any observer, no matter how long that observer is willing to wait. So in particular, the event horizon, by definition, cannot ever be detected in finite time. So if you're running a computer simulation, you can't ever actually figure out where the event horizon is in finite time. So if I hand you the universe at some moment in time, and the universe has a singularity, you in principle have no way of knowing if that singularity is inside an event horizon or not, unless you have the exact fine-grained equations of motion and you have all the computational power that you need to evolve them all the way to future infinity.
Sorry.
So this makes it, yeah, so is that question? Yeah.
Can there be, are these definitions equivalent to just saying the event horizon is just the surface where a certain metric is singular? I mean, is there like a more mathematical way of defining the singularity? Sorry, of defining the event horizon telescope in terms of metrics, for instance?
So the event horizon is defined as the boundary of the past of scribe loss. And that's the coordinate-free definition of the event horizon. And so there is, in principle, without having access to scribe plus, you can't know where the event horizon is. And in order to have access to scribe plus, you need to evolve the space-time for the initial data that you're given for all time. That's just by definition of the event horizon. In principle, you could come up with any number of coordinate systems which will be singular and vary in different places, and you won't know which one of those corresponds to an event horizon. Did that answer your question?
Yeah.
So we have a pretty inconvenient problem, and so searching for a version of cosmic censorship which is valid in nature, we could instead gain insight in the following way. We ask, what does a good version of cosmic censorship imply at finite time as well as for all time? In other words, what are the implications of cosmic censorship that are true at a given moment in time? So we don't have to ask what happens for infinite amount of time in order to figure out whether cosmic censorship is true or false, or whether some consequence of it is true or false. So what do we want? At least for all time, all good cosmic sensors will hide evidence of violent gravitational lensing from matter collapse. And they would minimize the amount of input that is needed from quantum gravity to continue evolution past the allowed small naked singularities. So that's what we expect a good formulation of cosmic censorship to imply for all time. And as an aside, classically, one of these is known as weak cosmic censorship and the other is strong cosmic censorship. And one elegant possibility is that quantum gravity implements both of these into one mechanism. Now, this is what we want for all time. Now for the hard part. What is a good version, what does a good cosmic censorship imply at finite time? And this is something known as the Penrose inequality. This is one implication of cosmic censorship that can actually be tested at a finite moment in time. So the Penrose inequality is a consequence of cosmic censorship that can be evaluated at a given moment in time because it concerns the apparent horizon rather than the event horizon. What is the apparent horizon? So let's recall some facts about light rays. So here I have a two-dimensional surface sigma in a four-dimensional space-time. There are two ways to fire light from this surface towards the future. So there's the ingoing future-directed light rays and outgoing future-directed light rays. And if I fire these from every point in sigma, then I will generate two null surfaces, the outgoing one and the ingoing one. Now, the way I've drawn these, the cross-sectional area of the outgoing one is increasing as we evolve forwards in time. Here, time runs in this direction. And the ingoing one has decreasing cross-sectional area as we evolve forwards in time. This is based on approximately flat space intuition. It tells us that future outwards should expand and future inwards should contract. In curved space, this is not always the case. Outgoing light rays can contract, ingoing light rays can expand. So in particular, near a black hole singularity, or very close to a big crunch, space-time volume contracts. Both ingoing and outgoing light rays contract. And because this is a local notion of light being trapped inside a region, we call surfaces where this happens trapped surfaces. And far from a black hole, ingoing null rays contract. So outgoing light rays expand. And these are the ordinary surfaces we see in our day-to-day life, so we call these normal surfaces. And so if we think of the black hole as being populated by trapped surfaces, and the black hole exterior is being populated by normal surfaces, then between the two regions, we have surfaces with contracting ingoing rays and outgoing light rays that neither contract nor expand. So the outermost surface whose outgoing light rays are not expanding, we can think of as the boundary of the black hole. And I'll have a picture on the next slide. So an apparent horizon is the outermost surface on a time slice whose outgoing light rays are non-contracting. So here I've drawn a picture there with the apparent horizon behind the event horizon on some time slice. So the light rays of the event horizon generically will be expanding if the black hole is dynamical. And the light rays deep inside the apparent horizon are contracting. The light rays on the apparent horizon itself are neither contracting nor expanding. And notice here the reference to a time slice. This means that this apparent horizon doesn't require input from future infinity. You can determine where it is at a finite moment in time. As an aside, non-dynamical black holes have the feature that the apparent horizon and the event horizon coincide, but generically that's not the case. Okay, so what is the Penrose inequality? So suppose we have a four-dimensional asymptotically flat spacetime with total mass m and an apparent horizon sigma. Total mass here is, just for those who are familiar, the ADM mass, which is determined at spatial infinity. A good cosmic censorship conjecture should imply that strong gravitational lensing lies only behind the event horizon, meaning that apparent horizons, which are a feature of strong gravitational lensing, will also lie behind event horizons. If you also assume that the area of an apparent horizon is smaller than the area of the event horizon on some time slice, which is actually a statement which is not always true, but it involves some technicalities that I won't go into just yet, so let's make those assumptions again. If you have concerns about this assumption over here, we can talk about it later. Now, we also know that, so then we have that the area of the apparent horizon is smaller than the area of the event horizon at some time. And we know that the area of the event horizon only increases with time by the Hawking area theorem. So this is going to be smaller than the area of the event horizon at final time. Furthermore, let's also, on top of that, assume that any black hole settles down to Kerr. Then the final area of the event horizon will be equal to the area of Kerr with mass m and some angular momentum j, which is always less than the area of a Schwarzschild black hole with mass m, which is equal to 16 pi m squared. Altogether, the area of sigma, which is smaller than the area of the final event horizon, is going to be less than or equal to the area of a Schwarzschild black hole with mass m. So cosmic censorship implies that the area of any apparent horizon is always has an upper bound in terms of the total space-time mass. And this is something that can be determined completely on a time slice. It's a time local implication of a cosmic sensor that hides trapped surfaces, that is violent gravitational lensing, behind horizons. So this is something we can check without knowing anything about the infinite future. And I should say a similar statement can be derived for asymptotically ADS spacetime. The power here, the coefficient will be a little different. So what's the current status of the Penrose inequality? Well, it's not so great. There are some proofs in the asymptotically flat Riemannian case, but there's no general proof for the Lorentzian Penrose inequality in asymptotically flat space, and even less is known about the asymptotically ADS case. Now, thanks to Horowitz, Santos, and Crisford, we now know that cosmic censorship actually can be violated for asymptotically ADS initial data. So we don't expect that we can prove Penrose's inequality for general asymptotically ADS spacetimes. So that might explain where we don't actually have a proof of it. But maybe we can have, solutions to GR that have a UV completion will actually satisfy the Penrose inequality. So we can't prove it using geometric facts about GR, but maybe we could prove it using something about quantum gravity. So does quantum gravity enforce the Penrose inequality? And the short answer is yes. So under a number of assumptions that I'll state in a moment, this was in a paper with Gary Horowitz in last year, we were able to prove the Penrose inequality for certain formulation of quantum gravity. So more precisely, there is at least one self-consistent formulation of quantum gravity, which is in principle non-perturbative, in which we were able to prove the Penrose inequality. And this is the ADS-CFT correspondence, also known as holography. I don't have time to really go into ADS-CFT, so I just want to make the brief statement of what it is. ADS-CFT is a duality between quantum gravity with ADS boundary conditions and a conformal field theory in fewer dimensions. And what we were able to do is we were able to use the dictionary that goes between the gravitational theory and the quantum field theory, in facts about quantum field theory, to prove the Penrose inequality in quantum gravity and ADS. So this is the statement that we were able to prove. So if sigma is an apparent horizon with some fine print that if anybody has any questions about, please ask at the end. I have a number of slides prepared also with the proof of this. So if sigma is an apparent horizon in an asymptotically ADS spacetime with mass m, assuming something called the holographic entanglement entropy proposal and ADS-CFT, the area of the apparent horizon is less than or equal to the area of a static black hole with mass m. And again, questions about the proof are welcome during the Q&A. So in fact, you can actually show something even stronger than this. This is current work in progress. That a consistency of the ADS-CFT duality demands that a quantum generalization of trapped surfaces always lie behind an event horizon. So this is really strong evidence in favor of a quantum cosmic sensor in at least one formulation of quantum gravity. So the last few minutes I will spend on the quantum cosmic censorship conjecture. Again, this is work in progress right now, so it is subject to change. What do we want from a quantum cosmic censorship conjecture? We want any naked singularity to be small by some precise measure of small, whatever that means, which would include.
Sorry, Netta, did you just say that you show? I didn't quite get that. There's always an apparent horizon inside an event horizon. Is that what you said?
So cosmic censorship would imply that apparent horizons lie behind event horizons,
right?
Not that every event horizon always necessarily apparent horizons behind it.
Right.
Yeah.
Okay.
So what we would want is that any naked singularity would have to be small. So by some measure that would include evaporating black holes and Gregory Laflamme, but exclude something like the Christopher Horowitz-Santos example, and would result in relatively little gravitational lensing outside of a horizon. So any naked singularity would not have a lot of gravitational lensing, so that trapped surfaces would not exist outside of the horizon as a consequence of these naked singularities. And the conjecture, roughly speaking, and again, this is subject to change as a tentative conjecture, is the following. This is work in progress with Rafael Busso and Maria Tomasevic. So if mg is a spacetime manifold, which is well described by semi-classical gravity, and let's also make it admit a UV completion in quantum gravity. So this is a conjecture at the end of the day about quantum gravity. Yeah, Andy.
Wait, you said, isn't by definition the horizon, you don't want trapped surfaces outside the horizon, but I thought by definition the horizon was the region of trapped surfaces. So you mean outside the event horizon or apparent horizon?
The event horizon.
But doesn't an evaporating black hole have trapped surfaces outside the event horizon because the apparent horizon is the...
That's right. So in spacetimes that violate the null energy condition, what we would want to replace trapped surface is a quantum trapped surface. So the quantum trapped surface is one where instead of the area being decreasing along the null congruence, the thing that decreases is the generalized entropy. So because we have because we don't have the Hawking area theorem anymore, or there are a lot of things we lose when we violate the null energy condition. We want to replace it by the generalized second law, which means we replace the area by the generalized entropy. So there will be a quantum, we will be talking about what I mentioned earlier a couple of slides ago as a quantum generalization of trapped surfaces. So it's just,
you don't want quantum, by definition, you don't have ordinary trapped surfaces outside the horizon, but you also don't want to have quantum trapped surfaces.
Well, we actually can have ordinary trapped surfaces outside of the horizon.
Yeah, the event horizon, yeah.
Out of the event horizon. And we want to make sure we don't have quantum trapped surfaces outside of the event horizon, yes. So Yeah, so here we have some space-time manifold, well described by semi-classical gravity, admitting a UV completion in quantum gravity. Now, because we're demanding that this manifold be well described by semi-classical gravity, it might have holes in it where the semi-classical approximation breaks down. We're going to excise any such regions, so we only deal with the space-time, which is semi-classical. And of course, that means that the space-time, the manifold itself may be extendable. So we are not assuming anything like global hyperbolicity here. Now, we are going to conjecture that these holes are always small in the following sense. So the generalized entropy of these holes, and I'll draw a picture in the next slide, which is given, so this is a quantity that is defined as a sort of quantum corrected area. It's the area over 4 in Planck units plus the entropy. We are going to demand that this object be order 1. In particular, what this means is that GR evolution can fail to be deterministic at most order 1 bits. So if you wanted to go from before the hole to after the hole, you would need to supply, quantum gravity would need to supply you with just an order 1 amount of information. So this is a statement about determinism of general relativity or semi-classical gravity. So here is a picture.
Sorry.
Yeah.
Can a hole be large enough to contain an apparent horizon?
So that, sure. So here's an example. So here's the evaporating black hole. And I didn't draw the hole here, but it's going to have to exclude something like this region over here, which is strong quantum gravity region. And here I have a spatial, so here's a spatial slice. And so right there. And they have the surface mu here. And there indeed exists a surface mu whose generalized entropy is order 1, where this von Neumann entropy of mu is measured on this thing over here. And mu contains in its interior the entirety of this small black hole. So the conjecture is that you can, any singularity which is allowed in quantum gravity, which is outside of an event horizon, can be contained inside a region which is essentially Planck-sized. So this is a precise way of saying that the singularity is small, that the naked singularity is small. And this appears to permit, I should say, we haven't checked quite thoroughly yet, but this appears to permit Gregory-Laflamme type instabilities, as well as the black hole evaporation endpoint, while forbidding more violent naked singularities that cannot be enclosed in a surface whose area is Planck-sized.
But here's so special about the 4-dimensional Planck scale. I mean, if you have plenty of other length scales around in your problem, why couldn't space-time, 4-dimensional space-time break down at a very different scale?
You mean why couldn't, okay, so yeah. So in principle, what I've written here is the area plus the von Neumann entropy, but are you worrying about something like higher derivative corrections or stringy corrections?
Yeah, I mean, Kaluza-Klein scale, string scale, there are all sorts of other scales.
So in that case, you would need to replace this object with something which includes the higher derivative corrections, and you would demand that the whole thing is order 1. And in that case, this would need to be, details would be a little bit different, but the generalized entropy would nonetheless, we would want it to be order 1. It would be a sort of a generalization of this generalized entropy, and ADS safety would be the Dong entropy. But yeah, this can include other scales if necessary. Essentially wherever the semi-classical approximation breaks down, that would be the appropriate scale to consider. So
okay.
Yeah.
And then these surfaces that you're describing, these quantities don't require you to talk about surfaces near the singularity. You only have to talk about surfaces outside the region you excite?
Yeah, only in the semi-classical regime. We don't know how to talk about surfaces that are in the quantum gravity regime, so we definitely don't want to be making conjectures about those. We don't know how to talk about geometry there.
But then when you're constructing these quantities in this semi-classical region, you still need to input information about the length scales that are far smaller than that.
So you need to have information about the low energy Lagrangian. So you would want to know what all of your cutoff scales are. And this generalized entropy, this is a quantity that, so far this is the way I've written it, it doesn't include any stringy corrections, but normally indeed, you would replace this area by a walled entropy, and you would have stringy corrections, and the generalized entropy would be defined in that way. So it depends on the theory that is describing your space-time. But the generalized entropy as stands is a quantity which incorporates all of the relevant scales. I've just written it here in the simplest form, which doesn't include any additional corrections. So preliminary results, which are quite preliminary, so that we haven't quite finished this proof yet, but preliminary results indicate that this is most likely sufficient to guarantee that trapped surfaces indeed lie behind event horizons, which means that we may be able to fold these two different aspects of cosmic censorship, that GR is deterministic and that naked singularities are invisible, into one quantum cosmic censor. So I think I'm probably out of time, so let me wrap up. So to summarize, the absence of direct observations of quantum gravity phenomena and matter collapse, as well as various other considerations, suggest that there might be a mechanism in quantum gravity that is responsible for hiding naked singularities from semi-classical asymptotic observers. And also a mechanism that guarantees that GR evolution can take place in a more or less deterministic fashion without much input from quantum gravity. Now this mechanism, a quantum cosmic censor, is difficult to formulate even in conjectural form due to the difficulties involved in defining what we mean by hiding, naked singularity, much input, horizon, etc. But regardless, even though it's been a long time coming, we do understand this mechanism, we do understand this cosmic censor better now. We understand that this is false in at least non-asymptotically flat 4D, non-4D GR. But most likely it is true in some formulation of quantum gravity. Now, quantum cosmic censorship has the potential to distinguish between solutions to GR that have a UV completion and ones that do not. So it has the potential to be a so-called swampland condition.
How does that work if the bound that you need, if you need to input data about the UV completion in the definition of all of the quantities in the inequalities?
You don't. You only need access to the effective theory. So you just need to have an effective field theory Lagrangian and know where it breaks down. You don't need to know how it breaks down or what is the UV completion. So
would it,
yeah.
Would it be a bad thing if this conjecture were false? I mean, it would just mean that that there might be situations in which we needed quantum gravity to predict stuff. That wouldn't be.
So
that would be good, actually.
It would be great for those of us who would really like to see quantum gravity in the universe. Like I said earlier, it's a bit of a double-edged sword in the sense that there is a slight question of it seems like we've looked and haven't seen it. On the other hand, maybe we haven't looked hard enough, maybe we haven't looked in the right place.
There is a more, I mean, one thing that is unclear is all these, the quantum gravity theory that you're talking about, it may preclude the existence of a singularity. There may not be a singularity. The reason we have a singularity in GR is because it doesn't have quantum mechanics. So you are trying to protect something that may not exist in quantum gravity.
Well, by singularity, I really mean strong quantum gravity region.
Yeah, but how do you know how it looks? Maybe it exists and you just misinterpret it.
I agree, which is why I think it's important to understand this conjecture and whether it's true or false. If it's true, then it's telling us something fundamental about quantum gravity. And if it's false, then it's telling us where we might look in order to actually see quantum gravity effects. So whether it's true or false, either possibility is fascinating. So yeah, let me just finish the summary here and then I'll take more questions. So some consequences of cosmic censorship have indeed been well studied. The existence of trapped surfaces outside of event horizons, is considered a hallmark of violations of cosmic censorship. And conversely, the Penrose inequality, which follows from trapped surfaces always lying behind event horizons, is a litmus test of cosmic censorship. Now with Gary Horowitz, he and I showed that quantum gravity in ADS indeed obeys the Penrose inequality. And current upcoming work with Rafael Busso and Maria Tomasevic quantifies the allowed naked singularities as ones that can be described by semi-classical physics up to an order 1 number of bits, which allows black hole evaporation or Gregory Laflamme. Preliminary indications also suggest that this may imply that trapped surfaces, quantum trapped surfaces at least, lie inside of event horizons, not evidence horizons, and by extension, the Penrose inequality, so folding both cosmic censorship conditions into one quantum gravity statement. So looking ahead, if quantum cosmic censorship indeed implies all that we would like, and if it is true, then we would be in a good place to begin the task of tracking down what is the fundamental ingredient or mechanism in a full quantum theory of gravity that enforces the quantum cosmic censorship conjecture, or the existence of a quantum cosmic censor. and in the longer term, potentially understand the deep physics in quantum gravity that is responsible for singularity resolution, and what happens in what classical gravity would call a classical singularity, and quantum gravity would call strong quantum gravity. So with that, thank you very much for your attention.
Thank you, Netta. Are there any questions?
Hi, Netta, thank you for the talk. I had a quick question. So from the mathematical perspective, cosmic censorship, weak or strong, is really a statement about what kind of open set can you find such that the dynamical evolution of that open set satisfies some property or other.
Yes.
So a statement of cosmic censorship, properly understood, is really just a statement of what we mean by genericity and what kind of open set are you able to find. In other words, cosmic censorship is only as good as the definition of genericity that you put forward. So I understand that assuming things like cosmic censorship, black hole stability, rigidity, one can propose something like the Penrose inequality. Of course, that's a very well-known classic thing. But I'm just wondering, in the quantum gravity kind of like scenario in which you work in which you operate and try to test some of these ideas, is there a stand-in notion for genericity? Is there something analogous to the concept of genericity, which is so absolutely central to the actual conjectures in classical GR?
Yeah, so I would say that in quantum gravity, the genericity condition, unlike in the classical gravity case, is simply not necessary. So in particular, I would say that at least the examples of violations of cosmic censorship, or maybe let's take a classic example of Weiser-Nordström, which would violate cosmic censorship, strong cosmic censorship, if it weren't for the fact that it's non-generic. And there's been recent evidence that if you consider even just a Hartle-Hawking state on the inner horizon, then that causes that results in a singular stress tensor. So you don't actually need to impose, it would appear that you don't need to impose a genericity condition in order to get a cosmic censorship conjecture that might be true in quantum gravity, as long as you're including quantum back reaction from the state.
So you're saying that the actual notion of genericity doesn't play such an important role in the quantum gravity scenario?
Yeah, exactly.
That's really interesting to know. Okay, thank you.
Yeah, Andy.
Yeah, thanks for the great talk, Netta. So in 4 dimensions, it's sort of the opposite of the question, or related to the question you're asking. In 4 dimensions, in asymptotically flat 4 dimensions, if cosmic censorship isn't actually true, it's pretty close to being true in the sense that 50 years of searching have failed to find any really robust counterexamples.
True by exhaustion, yeah.
Yeah, true by exhaustion. Do you have any thoughts on, and it's related to the question I asked you before, do you have any thoughts on why it should be true or why we would want it to be true? And I guess it's the same as the question of why what you're proposing should be true or why we'd want it to be true that I asked you a moment ago.
Yeah, so I think there's a bit of a conservation of misery situation here, where I think what's really interesting is that if you look at the arguments for cosmic censorship in, say, ADS-CFT, everything breaks down if you go to the flat space limit. And of course, we don't understand ADS-CFT all that well, or many aspects of it, when we go to the limit, to the flat space limit, which means that any insights that we get, and a lot of what I've said is motivated by things that we know are true in ADS-CFT. Everything that we say in that case is not clear exactly how it translates to asymptotically flat space. So it does seem that asymptotically flat 4-dimensional space is somehow special in many ways. And it would be
You should be happy about that.
I'm not sure what to make of it, because it seems to me that if there's a good chance that cosmic censorship as originally formulated is actually true. without need for input from quantum gravity at all, we don't need a quantum cosmic censorship conjecture for four-dimensional asymptotically flat space, which suggests to me that there's got to be some extraordinary circumstance or symmetry that somehow protects four-dimensional asymptotically flat space. And to be honest, I'm not 100% sure what to make of that. It doesn't seem from any other perspective like it should be special from four-dimensional asymptotically ADS, but somehow the two do seem to be quite different, and it's not entirely clear how. I think when we are better at understanding the flat space limit of ADS CFT, we may start understanding what makes 4D asymptotically flat space so special.
So just a little finger on that. So I think I think it's difficult to speak of these things and say that they're true or false. I think the point is that you look for an open set. So, you know, if I give you data that's very bad data, then you're going to find counterexamples. Christodoulou's found some. You know, it's about what you mean by genericity, and it's about what you mean by regularity. And the whole quest of modern mathematical general relativity is just to find an open set of examples. Like, we don't even have an open set of examples that forms a black hole that satisfies weak cosmic censorship for the Einstein vacuum system, say. Now, in the case of positive lambda, things are actually even better. So you can construct examples that satisfy a form of final state conjecture for the Einstein vacuum de Sitter case, so no matter field, just a positive lambda. Because Christodoulou's trapped surface formation result allows you to, it hasn't been written up, but it can be done, that you can form a trapped surface dynamically. And then once you've done that, you can add data and then use stability of Kerr de Sitter to move the space-time into the future and complete the space-time. And then you will get an event horizon, and you will have something which satisfies weak cosmic censorship in this setting. So flat space-time is more of a borderline case. ADS is definitely the naughty one. Positive lambda is the thumbs up one, and the flat one is really sitting on the boundary. That's how I would talk about it. In terms of weak cosmic censorship, at least. Strong cosmic censorship, a whole different issue.
I was going to say, I think there are now counterexample by Oscar Diaz and his group about strong cosmic censorship for de Sitter.
Yeah, absolutely. That's a whole different thing, yeah.
Yes, yeah.
But there is something curious about that case as well. So these examples of asymptotically de Sitter violation of strong cosmic censorship. These classical examples. There was a paper by Walden, Hollands, and friends which did show that, you know, if you even consider a little bit of quantum field theory in a curved background in those spacetimes, strong cosmic censorship can be saved by a much stronger divergence of say the energy momentum tensor of a scalar field at the horizon. So there is a little bit of the same spirit that Netta is telling us about in this talk.
So the Christodoulou argument is specific to 4 dimensions?
It was, well, that paper was specific to 4 dimensions, yeah.
Yeah, I mean, right now there's, so I'm working on this Christodoulou trap surface formation. Been doing so for the past year. We're currently extending it in various ways. So soon, I hope to be showing you guys some things of describing some of the things I've been talking about. But the point is that lambda is actually not relevant for Christodoulou's thing. For stability, strong cosmic censorship, lambda is really important. But Christodoulou's formation, lambda is not such a big deal.
Are you saying that we would expect the same argument to hold for ADS? Because we do know there are, well, at least Gary and friends have constructed counterexamples in ADS for, not vacuum though, sorry, this is vacuum, right?
No, but are we talking about the same thing? I'm talking about the trap surface formation result.
No, we are not talking about the same thing.
Okay, are there any other questions? Right, if not, let's thank Netta again, and we move to the next speaker.
Yeah, so I will be introducing Max. Max Zimet received his PhD in physics in 2019 from Stanford University. And a few months later, he joined Harvard and the BHI. And Max's research interests are mostly related to phenomena in string theory and field theory. And today he's going to talk about how to build a K3 surface. So please go ahead.
Thank you very much. Can you see my screen right now?
Yes.
Yes. Mm-hmm.
Okay, great. So this is a picture of K2. So the star of this talk is obtained by adding a K to K2. So you get K3. All right. So I'll tell you what K3 is soon. I'm going to tell you about work in progress. We're going to have this paper out in a couple weeks, I think, with Shamit Kachru and Arnav Tripathi, where we're going to give two explicit constructions of Ricci-flat K3 metrics. So let me first start off by motivating why string theorists care about K3. And this is very closely related to why mathematicians care about K3. The string theory naturally requires higher dimensions, and in particular, perturbative string theories generally start off with 10 dimensions. So you can think of this cartoon of string theory as being a machine where you take some solution of the vacuum Einstein equation, some Ricci-flat 6-manifold, you plug it into 10-dimensional Einstein gravity, and then via the Kaluza-Klein mechanism, it spits out a theory of 4-dimensional physics. And in particular, the theory of 4-dimensional physics that you get depends very strongly on the geometry of this Ricci-flat 6-manifold. So you can get a very wide range of phenomena in four dimensions just by choosing different geometries, different types of Ricci-flat 6-manifolds. And a special case of this is provided by what's called Calabi-Yau threefolds. These are special types of Ricci-flat 6-manifolds, and the reason we call them threefolds is because they have natural complex coordinates on them, and so it's natural to count in complex dimensions. And these are a very nice special case of Ricci-flat 6-manifolds because if you plug them into a supersymmetric version of 10-dimensional gravity, then you get supersymmetric 4-dimensional physics. And physicists and mathematicians like supersymmetry for a variety of reasons that I don't want to get into right now. So these metrics were conjectured to exist by Calabi and famously proven to exist by Yau, but this proof is non-constructive. And so the state of the art until rather recently was somewhat dismal, that no example of a Ricci-flat metric was known for any compact non-toroidal Calabi-Yau manifolds, and perhaps we shouldn't even exist such metrics to exist in closed form. And one intuitive reason for this difficulty is that Calabi-Yau manifolds don't have continuous isometries, and we're very good at taking advantage of symmetries of problems. So when there are no symmetries, life is much harder. So just an example of what some simple Calabi-Yau manifolds look like. The simplest Calabi-Yau manifolds are just tori. So here I've shown a 2-dimensional Calabi-Yau manifold. There are higher dimensional versions of tori that are again Calabi-Yau manifolds. The next most interesting Calabi-Yau manifold, and in two real dimensions, all there is tori. In 4 dimensions, all there is tori plus this extra case called K3. And so because of this, K3 is essentially the simplest non-trivial Calabi-Yau manifold. And we can build up Calabi-Yau threefolds out of K3. But yeah, this privileged place of K3 as the simplest non-trivial Calabi-Yau manifold has given it a very special role in string theory. It's central to essentially all dualities in string theory, for example. So that brings me to this slide. Depending on, so what is a duality? There are various situations in physics where there are multiple descriptions of that physics, and they're secretly equivalent, but they look very different from each other, and the relations between these descriptions are very non-trivial. So an example here is this picture where, depending on how you look at it, you might say it's a rabbit or you might say it's a duck. Frequently, both dual descriptions of some physical system will have some virtues, and you'll be able to learn something about the system from both pictures. And this has been a very fruitful source of solutions to problems in both math and physics, because you can often take some hard quantum problem that you don't know how to solve and turn it into a classical problem in some dual description. And so there's this sort of paradigmatic approach where you take a classical problem, feed it into a string duality, and you spit out the solution to some very hard problem that you didn't know how to solve. Now, sometimes this approach has been turned on its head, in particular in the approach to mirror symmetry proposed by Strominger, Yau, and Zaslow, where you can construct a classical geometry, a classical Calabi-Yau manifold, by studying some quantum counting problem on the mirror manifold. And in this spirit, I, with my collaborators in a previous paper, explained how, given the solution to some counting problem, we could write down a very explicit formula for a K3 metric. And you know, this counting problem is a much easier problem than writing down the metric. It's just out beyond what is currently known how to solve. I expect that direct approaches to solving it are not long from now, will not take that much longer to discover. But in this talk, I'm going to describe a different way of solving this counting problem, which is more in line with the original approach, the usual approach to dualities, which is we're going to study a classical problem whose solution will spit out these integer invariants that will yield the K3 metric. Now, of course, the classical problem here is the K3 metric itself, which is the thing we were trying to get. And so this is a very difficult classical problem. But we'll see that there is actually a limit in which we can describe the geometry of K3 surfaces exactly. So we'll end up with two equivalent but very different looking descriptions of K3 metrics in the end. Okay, so the starting point is just, this is called an orbifold limit of K3. Just K3 has a lot of parameters or moduli that you can tune, and in some limit, it looks like this this quotient space. So let me explain what this space is. You can construct a four-dimensional torus T4 just by taking the flat four-dimensional Euclidean space and quotienting it by some four-dimensional lattice. So just for any lattice vector lambda, you identify a point y in R4 with y plus lambda. So that effectively just restricts you to the unit cell in this lattice. And then you can further orbifold this T4 by an extra Z2 group just by identifying points y with their image minus y. And so K3 has a limit where it looks like this orbifold T4 mod Z2. And I keep saying orbifold to contrast it with manifold because there's some singular points. And these are associated to the fixed points of this Z2 action. So if I have a y which is half of a lattice vector, then I identify it with minus y via the Z2. But then thanks to this, I can identify it with minus y plus 2y because 2y is in the lattice. But minus y plus 2y is just y. So this means that there's a fixed point of this Z2 action on the 4 torus. And those are associated to singular points where the manifold is no longer smooth. And so the whole task is to resolve these singularities. So there are different ways of dealing with this. For a mathematician, the way you deal with this singularity is a bit of an arts and crafts project where you cut out the region near the singularity and then you glue in some other space, the Iguchi-Hansen manifold. And this, you can show that this Iguchi-Hansen manifold can be glued in such a way that you get a smooth K3 surface. For a physicist, things are much nicer because the things that are seeing the space-time, I mean, we as humans are trying to describe the space-time, but what we really care about is how strings see the space-time, as string theorists. And it turns out that strings see orbifolds as very smooth, perfectly nice geometries, just as nice as any normal smooth geometry. And so we don't need to resolve it at all. We can stay at the orbifold locus as long as we make sure we talk about how strings are seeing the geometry rather than point particles. And so this philosophy, starting with this orbifold limit and asking how certain objects in string theory called D-branes see this orbifold leads to the following characterization of K3 as the solution to this funny math problem. So I need to introduce a few ingredients in order to state this math problem. So first of all, we have the dual lattice lambda hat, which is embedded in R4. Yeah, Andy?
Wait, but the orbifold has a B field in it, right?
That's right.
So, but you're just doing the Einstein equation?
What do you mean by the Einstein equation here?
Well, you talked about Ricci flat metric. So the B field, there's some non-perturbative, that B field's important in the resolving the singularity in the orbifold, and you're trying to solve a problem that doesn't have any B fields in it, right?
Yeah, good. So here, this description that I'm talking about is given by D2 branes, let's say, probing T4 mod Z2. And this is just a hyperkähler quotient. This is just a classical moduli space of that D-brane system. And in particular, because we're on the Higgs branch, there's a non-renormalization theorem that tells you can take the strong coupling limit where you decompactify the M-theory circle, and the metric on the moduli space is unchanged. But in this decompactification limit, that B field dilutes away. So that tells you that the metric on the moduli space can't depend on that B field. So you're right. The UV formulation that we're using, the gauge theory relies on the B field being present, but the IR description, the metric on the moduli space, is independent of that. Okay, so we have so the starting point for this description is we have a dual lattice lambda hat, which is just the lattice of points whose dot product with any point in the original lattice lambda is an integer. And then given this lattice lambda hat, we can form the dual torus, which is just like before we formed R4 mod lambda. Now we form R4 mod 2 pi lambda hat. And then we study a SU2 gauge field, which I'll call A mu. So mu is a one form index on this dual torus. So if you're not familiar with the SU2 gauge field, this is just 3 one forms. One multiplying sigma x, one multiplying sigma y, and one multiplying sigma z, where those are the Pauli matrices. And then we have a constraint that a mu at some point minus y is related to a mu at some point y via this equation. We consider the set of these SU2 gauge fields which satisfy both this constraint and this equation on their curvature, so their field strength. So if I cover up this term for a second, this is just the anti-self duality equation, and then including these terms will modify that equation a little bit. So I'll call this the modified anti-self duality equation. And these etas are going to turn out to be the blow up parameters, which blow up the singularities at the fixed point. So when etas are 0, we'll have T4 mod Z2. We'll just have the flat but singular orbifold metric. And then when we turn on the etas, we'll resolve our space to a smooth K3 surface. And then the last thing we have to do is we have to only consider these gauge fields which are not identified by this following gauge symmetry. So we only consider gauge equivalence classes where the gauge group, the G is a SU2 gauge transformation, which is again required to satisfy this constraint. So this is sort of similar to the usual moduli space problems that one studies in gauge theory. There are just these extra funny constraints and this extra modification of the anti-self duality equation. So the punchline is, if we think of the space of gauge fields that satisfies this constraint as some infinite dimensional flat space, where, you know, it's not a very fancy infinite dimensional space, it's just a vector space with basis given by the Fourier modes, then the metric on K3 descends automatically from the flat metric on this infinite dimensional space, because we're just carving K3 out of that infinite dimensional space. So as a warm-up, just to get a sense of how all of these ingredients work together, let's just see how we get T4 mod Z2 out of this approach. So first of all, you know, when etas are vanishing, we just have the anti-self duality equation. And this quick calculation tells you then that the field strength is vanishing. And so this allows you to choose a gauge so that the A mu's are constants. So it's just a constant 4 vector times sigma x plus a constant times sigma y plus a constant times sigma z. Then we have to deal with a bit of extra gauge symmetry. So this gauge transformation allows us to assume that the sigma x and sigma z parts vanish, and we only have sigma y and sigma z parts vanish, and we only have sigma x. So now we just have 4 numbers, which are a mu, and these will turn out to be the coordinates on our K3 surface. And then the last gauge transformations we need to consider are these two. So this is a non-constant gauge transformation. These are the analogs of large gauge transformations in U1 gauge theories, and they implement the quotient by the lattice lambda. And the fact that these gauge transformations are well defined on the dual torus is when lambda is in the original torus is why we had to start with the dual torus. Because, you know, when, okay, I'll leave it at that. Well, when y gets shifted by a dual torus vector, then this changes by 2 pi I times an integer. And so but that shifts by the identity. And then lastly, this last gauge transformation, you can just see how it conjugates sigma x to minus sigma x. And so it implements the Z2 quotient. So we do in fact end up with T4 mod Z2 from when the etas all vanish. So now the idea is to study perturbation theory. We're going to turn on small values of these etas and find a nearby solution to the math problem. And that will give us explicit formulas for how to carve out the K3 surface from this infinite dimensional flat space. So at the first order in these etas, the Fourier modes of a mu all completely decouple, and we just find a simple linear equation, Fourier mode by Fourier mode, that determines each of these Fourier modes as a function of these a mu's. So as a function of the 0 modes, which are again still going to be coordinates on our K3 surface. So for the nth Fourier mode, we have some linear equation, Ln, this is just some matrix, which is a function of the a mu's, acting on the nth Fourier modes equals some constant vector, which is constructed out of the etas. Now, we can't invert that equation immediately because these LNs are not square matrices. We have more unknowns than equations, and so these L's have null spaces. And so the general solution is instead of this form where V is just some arbitrary element of this null space. And there's a good physical reason why these null spaces exist. It's because we haven't used up all of our gauge freedom yet. We've used up most of it in making these Q's small, but that condition is preserved by order C gauge transformations. And so we can just arbitrarily choose V to be 0, but because this is just gauge freedom. So we now have this solution for the Fourier modes to linear order in these blow-up parameters, and this carves out the K3 surface with its metric from the infinite dimensional flat space. And that was all at first order in the perturbations, but then we can continue iteratively to all orders by perturbing the perturbed solution and then perturbing that. Whoops. So at the nth order, you have the change in these Fourier modes is again given by the same sort of equation, where these L matrices are the exact same as they were before. The only thing that changed is this C now is constructed out of the nu minus 1th order Fourier modes. But this is, again, just some constant vectors. So you can just keep iterating this procedure ad infinitum, and you get the exact form of these QNs. And then you just write down the induced metric on the K3 surface given by this procedure. And okay, I don't want to unpackage all of this notation for you, but the idea of this slide is just to show you that we can very explicitly write down the metric. It's, we can plug it into Mathematica and see that it's Ricci flat. So this is at first order in the blow-up parameters. And it's a reasonably simple expression that you can play with very explicitly. So I've seen a lot of very impressive plots in my time at the Black Hole Initiative, especially from the astronomers. So I thought I would contribute my own plot. Here's the Ricci tensor. This is not numerical. It's just exactly 0. So I just plotted y equals 0. Okay. So
could you just go back to that key slide, the one before?
This one?
No, the one before that.
You don't have questions about this one?
Well, that one's easy to understand. So this is a formula for, this is a sum, n runs over an infinite number of lattice points, right?
That's right.
And
so these U's are just, U and V are complex combinations I formed from those A mu's.
For those A mu's. And the expansion parameter that's making this converge, or does it converge?
Yeah, the expansion parameter is these X's. These are the blow-up parameters.
These are the blow-up parameters. And they're getting, well, when we sum over n, why are they small? Why are they getting smaller? Why are terms would get smaller as we sum over n?
Yeah, there's a n inside of this d plus, so it's like 1 over n to the 6th.
Ah. So it's a series that converges like 1 over n to the 6th.
There's some n squareds up here, so I think it's probably 1 over n to the 4th.
And you could check you check this how on a computer?
Check that these formulas are.
Yeah. I mean, you derived it, but then you check, you put it into a computer and checked it. Is that what you said?
You can check that it's exactly Ricci flat, order by order. Yeah.
Order by order.
So at first order in the FI in these C's, it's exactly Ricci flat.
Okay, that's an amazing formula.
What do you mean by order by order?
By order, I mean two things. That's a good question. So I first of all mean at first order in the C's, it's exactly Ricci flat, but also the Ricci tensor decouples for each of these n's, and so for each n, the Ricci tensor vanishes. The contribution to the Ricci tensor from each n vanishes.
I don't know how you can do that, because Ricci tensor is a nonlinear operator in terms of the metric.
But we're working in perturbation theory around the T4 mod Z2.
Huh?
We're working in perturbation theory around the exactly T4 mod Z2 point. So,
okay, so perturbatively, you solve the perturbative equation 1 by 1. It doesn't mean that you solve the Ricci flat equation.
that's right. This is just an
Perturbative.
Yeah, that's
Yeah.
right. This is
So
just an
you
expression for the K3 metric in perturbation theory.
Yeah.
Next, Max is going to say how to get back to the K3 metric on actual smooth K3s.
But in perturbation theory, the small parameter is zeta, or it's 1 over n?
No. In perturbation theory, the small parameter is these C's. So,
Yeah, but the whole thing looks like it's. Then I would have. Why aren't I seeing a power series in the perturbation expansion zeta?
oh, I mean, there is a power series. This is just the order C squared term. This is the first order term.
Oh, this is the first order term.
Yeah, there's plus order c to the fourth in all of these equations.
I see. And how hard are those to compute?
I mean, they're not hard to compute. Like we can exactly write down what these CNs are.
Yeah.
So like, you know, at order c squared, we can write down what this guy is. But it involves an infinite series of the order c to the 1 Fourier modes. So you can plug this into a computer, but it's not as nice an equation to write down analytically. But you still can if you want to.
In particular, I want to emphasize that, so we have on the screen the order c squared corrections. The next order corrections are going to be c to the 4. If you want to solve for those are still finite dimensional linear algebra problems in each n. It's just that the coefficients of the finite dimensional linear algebra problems are going to be infinite sums of the expressions already on the screen now. So if you gave us like 20 days, just because that'll be how long it'll take us to, you know, get to grips with having to actually do it, we can certainly write down the next terms, but we're not going to unless someone forces us to.
Yeah. In particular, the Ricci tensor is very nice at first ordering C because we're expanding about this flat limit. So there's a contribution from the Christoffel tensor squared, but that's higher ordering C, so we get to ignore that. So things are very nice at this ordering C. And okay, I'll mention this, but because this came from a hyperkähler quotient construction, we automatically also get all of the complex structure matrices and all of the Kähler forms, not just the metric. And we can show, again, that the complex structures obey all of the properties they have to obey. So they behave like the quaternions, you know, I squared is -1, ij equals k, etc. And you know, all the compatibility conditions between the Kähler forms and the complex structures and the metric are all satisfied. Okay, so those are some those are one set of formulas. If you're familiar with our older work, they look nothing like our older formulas for the K3 metric, but by manipulating them via what's called a Poisson resummation, you can show that they exactly take the form predicted by our earlier work. And you can then read off from those expressions the integer enumerative invariants, which determine the metric in the other approach that we gave. And so this gives a very succinct equivalent way of describing K3 metrics. And yeah, in a particular.
Just sorry, one more question. So Page talked about, or maybe Page got it from some mathematician, I don't know, but about just gluing in the Iguchi-Hansen at the fixed. And that gives the right answer to first order and perturbation theory, right? But then you would have to have solved a complicated PDE to correct that, right? And what's different here is it's all algebraic.
Yeah, exactly. There's no yeah, I mean, like if I'm willing to say that I'm willing to take the solution of some PDE, then already Yao's theorem is enough, because that is also some solution to some hard PDE.
Well, but Yao didn't give us a method of a perturbative method of approximating it.
Yeah, that's right. So yeah, so the Page approach requires you to do this gluing problem. So you can show that you can get limiting descriptions of K3 surfaces by solving some gluing problem, but we don't know how to do that explicitly. This actually makes it very explicit. And in particular, we can show near the corners that it looks like the Iguchi-Hansen manifold, just like away from the corners, it still looks roughly like the flat torus. So yeah, you might say that this gives a very explicit algebraic way of implementing Page's idea.
And why should we expect to be able to reproduce a PDE problem into an algebra problem?
Yeah, I mean, so.
Is that a big surprise?
Yeah, I thought so.
Does that surprise you, Yao? Maybe he's not on. Okay.
Yeah, it boils down ultimately to the fact that at this first ordering C, all of the Fourier modes decouple, and so you can you just have this finite dimensional linear algebra problem. And yeah, we rely very strongly on the hyperkähler quotient construction. So one would not expect the same approach out of the box to work for Calabi-Yau threefolds, for example. Although we do expect it can be generalized to all known compact Calabi-Yau manifolds and possibly some new ones. So that's work in progress.
All compact hyperkähler manifolds?
Yeah. Okay, so in conclusion, I've sketched for you one very explicit set of formulas we have for describing the K3 metric in terms of what's called a hyperkähler quotient construction. There's an alternative formalism based on some integral equations written down by Gaido, Moore, and Knightsky that we've shown are exactly equivalent. And in fact, you can show that this iterative approach that we have for exactly getting the metric order by ordering C exactly corresponds with iterating their integral equation order by order around the semi-flat limit. So it's sort of funny that these two different expansions agree with each other. And yeah, as I mentioned, we're excited about a large number of generalizations, both studying other orbifold limits of K3 surfaces, as well as studying other compact Calabi-Yau manifolds. Yeah, I'll stop there. Thank you.
Have you proved convergency of this series?
Of this series?
Well, there's infinite. Yeah. Have you proved convergency?
The numerator is like n squared, and the denominator is n to the sixth. So this converges very well.
Well, it could still diverge. I mean, have you rigorously proved the convergency of the whole thing?
We haven't looked at that. I don't think it would be hard though. But yeah, we haven't looked at that yet.
Yeah. Can you use the metric like this to compute something like geodesics or minimal surface and all that?
Yeah,
I think only after that I can be convinced that it's a metric.
Yeah, I expect that it will actually be
properties that we know. What?
I expect it will be rather easy to study properties about geodesics in this approach because there are other papers that have already used hyperkähler quotients to study geodesics to great effect. And the idea is that geodesics on the K3 surface descend naturally from geodesics on the flat infinite dimensional space you started with. So yeah, I'm optimistic that we'll be able to study geodesics. Minimal surfaces, I'm less positive about.
Okay, let me mention a testing case, which I think very few people know. Many years ago, I mean 50 years ago, actually, I tried to disprove the Calabi conjecture. I proved if there exists a stable closed geodesic on the KP surface, if you take the KP surface as the covering of the NMP surface, you will find a stable closed geodesic there. So in Venner under the involution, along this closed geodesic, the curvature tensor turns out to be 0. This we can prove, and if you can construct such a stable closed geodesic and actually prove the curvature tensor is identical to 0 along this geodesic, then I'm convinced that you actually found this metric.
Okay.
Otherwise, I'm still skeptical.
Yeah, I don't.
Why aren't you convinced? They put it on a computer and it satisfies the equations.
Many people have done that, and I never trust on complete numerical solutions.
Well, this is not at all numerical. This is like analytical. This is exact.
Yeah, I agree.
The exact expression at order C squared.
Yeah, you have to prove the convergence before I'm completely convinced.
Okay. Yeah. I don't think there would be any difficulty in studying these geodesics at order C squared. That we should be able to do very explicitly, I think.
That'd be good. That'd be great.
But I also expect that I mean, this is certainly something we intend to do, that one should be able to rigorously prove using the usual techniques that mathematicians have developed for studying moduli spaces of solutions to the Engels equations, that this is indeed a smooth, compact hyperkähler form manifold. And then by virtue of its Ricci tensor not, sorry, the Riemann tensor not vanishing, it's not a torus.
Yeah. Good.
Any other questions? Okay, thank you.
Thank you. Nice talk.
Thanks.
Thank you, Max.